Welcome to the problem solving session for the NPTEL course on Theory of Computation. Okay, so in this week we'll focus on non-deterministic finite automatas. We saw the model of DFAs last time, and maybe we'll talk about regular expressions. Okay, so to begin with, how do we define NFAs? So NFAs are generalization of DFAs. And how do we define it? It is a 5 tuple again. So Q, sigma, delta, F, and the start state. Okay, and can someone recall how do we define the transition function for NFAs?
So that used to be Q cross sigma union this epsilon and maps to 2 raised to the power Q.
Right. So this is the power set of Q. And how is this different from DFS? In DFS, you are only allowed to go to a single state Q, whereas here you are allowed to go to a subset of states, which could be empty. Okay, so let's and all the other definitions remain the same. This is the set of final states, and you are allowed to make epsilon moves. That is, if you don't read a 0 1 or a symbol in sigma, you may still have some transitions on empty string. We'll see more about this as and when we come across the examples. Okay, so to begin with, here is an NFA that is given to you, and we want to read the string 101010 and find out what is a computation tree for it. So I'll maybe just do the first one to recall. Okay, so how do we define a computation tree? So initially you are at state q1. Okay, when you see a 1, what are the transitions that are possible? Either q0 stays at q0 or q0 goes to q1. So there are two possibilities. So we'll branch out from here. On 1, we can either go to q0 or we can go to q1. And we have read this one. Next, we are going to read a 0, and from q0 on 0 you can go to q2. So we'll add a transition like this. From q1 on 0 you can go to
Shouldn't the start state be Q0?
oh right, sorry, this is q0. Yeah, thanks. Yeah, and from q1 on 0 you go to q2. That is the only possibility. So we have only read 10 so far. So can someone tell the next step?
Q2 on seeing 1 goes to Q1.
Yeah, correct. That happens for both of them. Yeah, then you read a 0. Okay. Yeah, so basically on 0 you go to q2. That is the only possibility. And now you read a 1, so you go to q1 again, and again on 0 you go to q2. Okay, so is this clear? Okay, so can someone quickly tell what is the tree for the second NFA? Okay, I'll write the string also. So the string is 101010. or maybe let me just keep it shorter. Let's say the string is 1010 and you're starting at q0. So on reading a 1, where all can we go?
Q1, ma'am.
Yeah, q1.
When we read 0, goes to Q1. Then Q1 say.
So what I'll do is I'll take this step also, where from q1 you can go to q2 on reading an epsilon.
Yes, ma'am.
So I'll take a closure and write it this way. Yeah. Now from q1 or q2 on reading a 0, you can be at q1 or q2. So there may be repetitions here which will keep it like that. We won't merge it because it's a tree in the end. So, okay. So this is for 1, this is for 0. Then you read a 1. So what happens here is there, okay, you go to q3, and from q3 there is no transition on 0. Okay, so you terminate this path.
Yes, ma'am.
Okay, and when do we say that an NFA accepts a string? If any of these paths that we just do, so this was a very linear thing, but this could be a very large tree. So when do we say an NFA accepts a string? If one of those paths leads us to a final state, which is in this case we reach at q2 in at least one path, so we will end up accepting this string. Okay. Are there any
Okay.
questions? Okay, good. So we'll move on to the next question. Mm, yeah, so this is a question about understanding the basic definitions of NFAs and DFAs. So read out the statements 1, 2, 3, and yeah, and choose one of the answers. Yeah, you can
And
either.
option two.
Statement 1 only.
Okay. Yeah, anybody else if you have other answers?
So I think that the statement 2 is correct, but then that is not an option here because every DFA.
Yes, ma'am. Statement 2 is correct only.
Okay. Um, no, so statement 2 says that every NFA is a DFA, which is not the case because, for example, NFAs allow epsilon transitions, but DFAs don't.
That's right. That's right. I said in the sense of the power. I mean computational
Yeah,
power in that sense.
but yeah, so the statement here, as it is not about, yeah, whether we can come up with an equivalent DFA, but I mean, just that if I give you an NFA, then as is it a DFA?
Oh. So I was under the impression that if I do not exploit choice, by default DFA is an NFA. And for every NFA, since we can construct the DFA, so that the option 2 seems to be right.
Okay,
But
yeah,
that is not the case
hmm.
here, right?
Yeah,
Every DFA is a NFA,
yeah,
but not
correct.
every NFA is an DFA.
Sorry, but what? Um,
Option 1 is correct, and
yeah, that is correct. So the correct answer is option 1, that by definition, a DFA is an NFA where we don't exploit the choices. We just do a deterministic computation. Yeah. Yeah, and in terms of power, like Goel said, they are the same in the sense that every language that is computable by an NFA is also computable by some other DFA. Okay. So only statement 1 is correct. Good. So yeah, now what we'll do is let's look at this language L1, which is the set of all strings that begin and end with 101010. Okay, maybe for the sake of simplicity, let me just make it 1010. Okay, so can you come up with an NFA for it? Yeah, if you have one in mind, then just let me know. I'll draw it.
Yes, ma'am.
Go ahead.
So, I mean, for this 1 0 1 0, you draw a skeleton, say, for the Q naught. So, after getting a 1 1, make a move to say Q1,
Hmm.
and after getting a 0, make a move to Q2.
Hmm.
After getting a 1, make a move to Q3, and after getting a 0, make a move to say Q4. And now the string may begin either with a 0 or a 1. So, over the Q naught, use the self loop, say, irrespective of whether you get a 0 or 1. So, over the Q naught,
Q3 is the final state.
1, and you can mark this Q4 as a final state. So, yeah, I think that this NFA is sufficient to recognize the language.
Mm, okay, so this NFA will accept all the strings that end in 101010, but
Ah, okay, begins at
मैम
Q.
वन फर्स्ट स्टेप पे वन पे सेल्फ लूप नहीं होगा.
correct, yeah. So you won't have a self loop here because this is not detecting the that the string begins with 1010. So how do we modify?
ऐसे में लास्ट वाले पे सेल्फ लूप हो जाएगा. फाइनल Q4 फाइनल
Okay,
स्टेटमेंट सेल्फ लूप 10.
okay.
इसमें
Mm,
इट इज NFA.
so yeah, now this is detecting that the string starts with 1010, but it is not detecting that it ends with 1010.
एंड्स विथ मैम एंड्स विथ के लिए मैम ऑल एक न्यू क्यू नोट लेंगे. उसके बाद जो इसके ऑल स्टेट हो जाएंगे एंड्स विथ.
So you're saying something like this, we'll check for 1010 from here.
मैम मैम लास्ट से स्टार्ट करना होगा उसके लिए शायद.
Mm, as in from Q4 or
मैम एक न्यू स्टेट ले सकते Q4. न्यू स्टेट फाइनल ले सकते और एक दूसरा बनाएंगे उस पर इसको ज्वाइन कर देंगे क्यू नोट से.
mm, you're saying so this is a new Q0. This is what you're saying?
मैम नो मैम आई डोंट से दिस.
Mm-hmm.
Ma'am, I want to say, if we make new NFA,
Okay, sure. Maybe I'll call it P0. Okay.
yes
And
ma'am,
okay,
and
this is
मैम
what you're saying.
Q नॉट पे 10 yes मैम A और फिर यहाँ पर लास्ट लास्ट पे सेल्फ लूप में लगाएंगे सेम रिपीट हो जाएगा.
Okay, now
yes मैम और Q4 फाइनल है.
how do we connect these two?
न्यू स्टेट से कनेक्ट कर देंगे इसको और इसको एक न्यू स्टेट से Q नॉट को कनेक्ट कर देंगे दोनों को एफ फाइनल से.
Okay,
F
so you add an epsilon transition from. Okay, sure. This is the new start state.
Q.
Uh,
But
you
this
want
this
it to accept if both of them. Sorry, go ahead. Yeah,
एम Q4 फाइनल होगा सेकंड वाले में.
P4 you mean. Yeah, but now what will happen is it will accept strings of this form 001010 because it will make an um, yeah, it will make an epsilon transition here and then skip over the two zeros and check for 1010.
So why don't we use two skeleton, like say 1 0 1 0 1 skeleton, and then self loop over a middle state 0 comma 1, and then from here again continue, say 1 0 1 0. So there would be 1 2 3 4, all states in serial in a line. Only one state would be having self loop of the combination of 0 comma 1, so that every string begins with 1 0 1 0, and then we can have any combination of the zeros and the ones, and then followed by that stuff, the 1 0 1 0 again.
Hmm. So, so what you're suggesting is that we go and detect, sorry, we go and detect 1 0 1 0, and then we
Yes.
skip over zeros and ones.
Don't make it as a final state because we need to recognize end. I mean,
Hmm.
begin and end. Yeah,
Hmm.
that sort of.
Then
And again,
one
continue
zero
with 0 1
one
0,
zero.
and eventually make the last state as the final.
Ma'am, in this case, if start not start with 1 0 1 0 1, that मतलब अगर कोई स्ट्रिंग 1 0 1 0 से स्टार्ट नहीं है और वो एंड है 1 0 1 0 से, तो वो एक्सेप्ट नहीं होगी इसमें।
Uh, yeah, that is correct. So you are saying 1 0 1 0 itself is not being accepted in this example, even though it should get.
यस मैम।
Hmm.
Oh, I
So,
see. Yes.
hmm. So I think this will work if the input is large enough. So you will probably have to add several more transitions to detect smaller strings. Those can be, maybe, I guess you need to go up to length 8 or something. But if I have to modify this one slightly, if we make Q4 and P4 both non-final, so let me just do that. So Q4 and P4 are non-final, and then if I add epsilon transitions to a final state, this should work, right? um,
Ma'am, if we connect P3 to Q4 directly with 0, P3 to
mm,
Q4.
yeah, okay. uh, yeah, but then you are losing this information that it ends in 1010. If you connect it
No,
like
ma'am,
that.
P3 to 0. This is on also a final state Q4.
This thing is, this is what you're saying, remove P4 and make it 0. That's, yeah, both are same.
No, ma'am, I want to connect P3 to Q4.
On 0.
Yes, ma'am.
Yeah, that's what I'm saying. Then you will lose the information that, so let's say I'll draw this with red. If you do this, then you are accepting all the strings that end in 1010 followed by anything
Yes,
else.
ma'am. Yes, ma'am.
So,
Yes, ma'am. I know.
yeah. But yeah, this you can do. Here you can just directly add a, sorry. Here you can just directly add a 0. This is fine. Okay, so this one will require some modification, but I believe by adding some more transitions, this should work. The idea is fine here, but this is, yeah. Is everyone convinced that this is the answer for L1?
I have little doubt here
Hmm.
that because here an or, I mean, a union kind of the thing is being realized,
Hmm.
not an and kind of the thing.
Yeah,
So this is
that is
going to
correct. Yeah.
accept, yeah, that is going to accept some strings
Hmm.
which may not be part of the language.
Hmm. So then we'll have to make sure that it reaches both of them. Okay. Mm. Hmm.
Yes, ma'am. It is work for one word.
Hmm.
Not.
Yeah, this is sort of a union thing. Mm. Okay, but there is a standard trick for the intersection of two NFAs, right? Um,
Yes, so that would be that you make the final state of the first machine
hmm.
uh, you connect the final state of the first machine to the initial state of the second machine. Run both the machines not in parallel but serially. So, and X is the element of L1 intersection L2. If X is the element of L1, should reach till that point, and X should be the element of S2 as well. So we would be running both the machines in sequence, not in parallel.
Okay, so you're suggesting that we should identify Q4 with P0
Right. And
and
Q4
make the
with
final state.
zero thing, and then you use an epsilon move, kind of.
Hmm.
So the only issue in that case would be the acceptance of this string 1010 only,
Hmm.
and with beginning as well as ending with
Hmm.
this
Ma'am,
thing.
Q4 we can final Q4.
Sorry,
Oh,
can you repeat? Hmm.
मैम Q4 को फाइनल करके एप्सिलॉन ट्रांजैक्शन करके उस पर रिपीट कर सकते हैं नेक्स्ट वाले स्टेज के लिए 10 को.
Yeah, yeah. So you make this a final state and you make an.
नो मैम एक
Sorry.
फाइनल स्टेट करेंगे उस पर रिपीट कर देंगे. अच्छा हाँ इस पे भी कर सकते हैं.
Yeah. So this is not final yet. Sorry. Yeah.
10 हाँ ये तो हो जाएगा. And P4 also final state.
Yeah. P4 is a final state.
I think this will work.
But now that is this complete and final, or something else need to be done here? Because still this is not accepting this 1010. This is not right.
Hmm. Yeah, but if we are using the standard trick, then this should have been correct. Okay? Just give me a moment. Let me see.
And if Q4 is final, then 1010 accept it.
Yeah, but then it may end up accepting other strings that we don't want. For
Oh,
example,
yes.
101000. Hmm. Hmm. Okay, so let me come back to this. Okay, I don't
Ma'am,
know.
ma'am, if we uh, if we accept only 1010, then uh, we uh, we take a new state Q5 where we repeat it epsilon epsilon transition and Q4 पे repeat कर देंगे then और then another state से उसको P0 से connect कर देंगे. हम we take a state
Yeah, so
Q5
yeah,
Q5
so
null transition.
yeah, so you can always do that fix. You can. There are only finitely many such things where this issue will occur. So you can pre-process and add those transitions and detect those strings separately. Otherwise, something like this will also work.
I,
So,
I, I have a small suggestion here.
hmm, hmm,
That the standard method is not working here because
hmm.
either of L1 or L2 could be a phi, could be an epsilon,
So by
right?
second method, what do you mean?
So I mean the standard method of
Correct. Okay,
combining
sure.
the two machines
Hmm,
is not properly working here
hmm,
because either of the
hmm,
L1 or L2
hmm,
could be an epsilon. So let us do
hmm,
one thing. You remove this S, epsilon moves from S,
hmm, hmm,
and you directly make Q naught as the initial state. Remove both the epsilon moves in the beginning of the first design.
hmm,
And then you start from the initial state, say Q naught,
hmm.
and then you add a epsilon move directly from Q0 to Q4. And yeah, make an epsilon move like this. And then there is other, so in this way. So in this way, I would be able to accept 10, 10. And I would be able to accept the second thing as well, wherein starting with 10, 10 and ending with 1. Yeah, this is correct now, I think. You verify this.
Okay, so sorry. Yeah, but now it will accept something like 001010.
Which one? 00? Tell me.
So you
What is
make an epsilon. Sorry. Uh, so let's take this same string 001010.
Yeah.
It will make
So
an
this
epsilon
is
move
epsilon move, right?
and make another epsilon move and start here at P0. Uh, Skip over the first two zeros and then read 101010 and reach at a final state.
Ma'am, we can try it. Ma'am, Q4 connect to another Q5 epsilon. Uh, Q4 connect epsilon. Ma'am, Q4 final and 10 transition. मैम इसको हटा दीजिए. Remove 10 transition self to and Q5 connect to P0 epsilon से.
What about this?
इसको remove करना मैम. Q5 से कनेक्ट करना और Q0 Q4 एप्सिलॉन रिमूव करना.
Q0, Q4, okay. Okay.
This can work.
Mm,
मैम Q5 self loop 10. No मैम it's to the work.
yeah, again this. Okay. So this will accept 1010. Okay. Yeah, but what about 101010 for example? That is not being accepted.
SMD did not work.
So let me do one thing, okay? I'll get back to this method one, but let me just uh, let me just say a couple of things about this method 2, okay? So the issue with method 2 is that if any string is of length 8 or larger, then this method will work. Does everyone agree? Because you have already detected that it started with 1010, then you have skipped over the middle part, and then you are detecting that it ends with 1010. This is non-deterministic because at this state there are two possible transitions. If you see a one is that either you stay here or you go to the next state. So this is an NFA. Now the issue with this is that, so if length of string x is greater than 8, then this method works. The issue is that if the string is smaller, such as 1010 or 101010, then we are not able to detect. So what I'm saying is these are finitely many strings, so you could separately detect this and handle it separately. So that is one way to fix this. But yeah, I think that there should be something here that is easy and fixable. But yeah, I think I'll take some time and get back. But I hope that everyone agree that uh, this NFA with a few modifications will work. So for example, I could add transitions like this, and now make 1 0 1 0 1 0 accept.
Yes, that's right.
Okay, so these are like finitely many such corner cases, and you can handle it separately by adding more transitions. But yeah, let me check this out and get back. Okay, but yeah, good. Does anyone have any questions about this L1 NFA? Okay, so if that is clear, try for L2. So L2 is the set of all strings that has even number of zeros or odd number of ones.
That should not be difficult. Now we can, from the starting state, we can take two epsilon moves. Upper branch would be accepting even number of the, and the lower branch is the odd number of the ones.
Even number of zeros, right? Yeah. Sorry.
Odd number of. One more state needed. So from in the second branch,
Odd
say
number
after
of
getting,
ones.
yeah,
Mm.
after getting one, no, not like this, not like this. After getting one odd number of the ones, right? So after
Yeah.
getting one, we came up to the state. After getting one more one, we came up to one more state, and then
Uh,
from
yeah, so
odd number of ones.
no, this is fine, right? So if you go here on getting one occurrence of one, you are accepting it.
Yes, so one, two, three. Yes, yes, right, right, right. Yeah.
Okay. So what did we do? This part here, um, this part is the DFA for even number of zeros. This is what we did last time, and this part here is the DFA for odd number of ones. Okay, and we want to accept union of these two languages. So this is what we did. We made an epsilon transition from the start state to both of these. So in at least one of the two computations it will get accepted.
Yes.
Okay, so this is the general trick that we have. If you have an NFA N1 and you have an NFA N2, and we want NFA N for L of N1 union L of N2, then what you do is you create a new state, add epsilon transitions to the start state of N1, the start state of N2. Yeah. Okay. So is this fine with everyone?
What if we have an and here instead of or?
Yeah, that's the issue we had earlier, no? If you want an intersection.
But then this won't be that difficult because there won't be the strings
Yeah,
which are
this one is not difficult because you can do a product construction sort of thing.
product is fine. Product is fine because the construction of the DFAs would be easy for for both the languages.
Hmm.
But like in this case, if we use, I mean, the first problem, the problem was there because
Hmm.
one string became the part of L1 and L2 both,
Hmm.
or the portion. But here that won't be the case because
Hmm.
there are two separate languages, either the even number of the zeros or the odd number of the ones.
Hmm.
So that would be straightforward, I guess, if we go for the serial combination of the machines, like see combining these two machines sequentially and by using the apps. That would be the case of concatenation, I guess. L1 dot L2, not L1
Not, yeah.
and intersection.
Hmm.
Yes, yes, right, right. For the intersection thing, we do not have the standard method, and probably this is maybe captured using what? L1 intersection L2 can be viewed as a complement of L1 and the complement of L2 and then take its union. That sort of thing.
Yeah, but getting a complement of an NFA is not easy. Um, because in the case of DFA, if you want a complementation, you'll just switch the final states and non-final states, and you have your complement DFA for the complement language. But for NFA, we can't do the same trick directly.
Right, yes. So does this mean that whenever this either the intersection or a flavor of the intersection is coming, then we'll have to we cannot think in terms of the NFA, and even if we think in terms of NFA, that has to be converted into the DFA first, and then we can go for that mechanism, the product automata stuff, to get the intersection or the complement.
Yeah, that is one way to do it. I'm not sure if there's a simpler method. Yeah.
Okay. All right. Yeah. Because for the NFAs, the common, I mean, usually used diagrams are for the union and the concatenation and for the claiming user. Three.
Yeah, that, yeah.
Right. Thanks.
Okay, so let's try for L3. L3 is the set of all strings that contain 101 as a substring before reading the last three symbols. So the last three symbols could be anything, but you want 101 here, and it could be preceded by anything.
So that would be like I can start with yeah. So I draw one state and having 0, 1 and 0, 1 self loop. Uh, and what do we want? I forgot the question. 101 and then
Yeah, you want 101 followed by three
yes,
symbols, and it could be preceded by anything.
right. So that has been captured here. And now writes for one, make a transition for one, make a transition for 0, make a transition for one, and then you make a transition for 0, 1.
Yes, ma'am.
The
Zero
next.
one, three transition for 01.
Yes, right.
Yes.
And make the last one as the final. Yeah, final state.
Oh, good. Yeah, so basically what we're doing here is we are skipping over the first part non-deterministically. Then we are checking here that there's a 101, and here this could be anything. Good. Okay. So B and C is clear. For A, I'll see if this can be modified. Okay. I'll come back to this question later. Okay. So okay. So you've seen that NFAs are equivalent to DFAs in the sense that um, any language that can be uh, accepted by an NFA can be accepted by some DFA. So if you are given an NFA with M states and you are converting it into a DFA, and let's say it has as minimum states as it can have, then what is the relation between the number of states of this DFA and M?
Ma'am, D option.
Option D. Yeah. So why is this? Because in the method you are, let's say you have,
Ma'am, we can take any number of M at the time. MC0,
you can take
MC1,
any
MC2.
subsets of this set. So the states in the DFA are, then you have 1, 2, 2, 3, and so on, all the way up to 1, 2, 3 up to M. So these are 2 power M many states. So at most it can have 2 to the M. Some of this could be redundant, so we can remove those and find a minimal one, but This is the maximum number of states you can have in a minimal DFA. Okay. Are there any questions?
So this is not, this is okay in the sense, but in the sense that, but in an equivalent DFA, we can have lesser number of the states also. This is not always necessary that the number of the states will always increase.
Yeah, you can have lesser number of states, but there are examples for which you will need 2 to the m states.
That's true. That's true. 2 raised to power m is the upper bound.
Correct.
So quite possible that in the minimal DFA we can have even, there could be a case we can have even lesser than m number of the states. That value could also be even less than m.
Yeah, but not for all DFAs.
Not for all. Yes, that's true. That's
Hmm.
true. And here, fortunately, they have not given that. They have skipped that option here. For less than thing, they have given either m square or 2 raised to the power m.
Hmm.
So if it is instead of say k is less than or equals to, instead of m square, if it is k is less than or equals to m, that could also be true in some
Yeah,
con.
so that's what I'm saying, that this cannot be true, because if you say that you can, no matter what NFA I give you, you can always come up with a DFA, equivalent DFA with k states, then that statement is not correct, because there are examples for which, given an m state DFA, NFA, you require 2 to the m states DFA.
Right. Yes.
Okay, good. Are there any other questions?
So is there any other method except this subset construction method to convert NFA into DFA?
Um, I'm not aware of any other methods. Yeah.
Okay. Okay. All right.
Hmm. Yeah, okay. One thing that you can do is, from DFA you convert to an NFA. Sorry, from DFA you convert to a regular expression using Arden's theorem or something. Then we know that a regular expression can be easily converted to to an NFA, because whenever you see, um, yeah. So from DFA you convert to a regular expression, and from regular expression you can go to an, sorry, yeah, sorry, this won't, yeah, yeah, eventually. Yeah, in order to get to regular expression also, first you need the DFA. We can't directly go from NFAs to the regular expressions. Yeah, sorry. Okay. Okay, so I'll move on to the next question. Yeah, uh, so try this out. So let's say that L is a language that is recognized by an NFAM, and now we are constructing a new language, reversals, which is the reversal of all the strings in L. So for example, if L is 0011 and 010101, okay, then the reversal language will contain the reverse of this, which is 1100, reverse of this, which is 101010, and so on. So you look at every string here, reverse it, and put it into this language. So this is what the language reversals is. And the question is this language regular? That is, can you come up with an NFA or a DFA for it?
So, so if 110 is to be recognized, then I am starting from initial and reaching to the final. So in this reverse, I should start from final and reach to the initial.
And
So I will want, yeah.
if we reverse all the transition in final to uh, initial state.
Yeah,
Yes, that's right.
that is correct. So let's say you have, I'm writing this very informally right now. Okay, let's say you have um, transitions like these, and then there are some final states that you reach. Okay, so what you're suggesting is that, let me call these p0, p1, and so on. So what you are suggesting is that we'll make these final states as our start state. So we'll add some epsilon transitions, p1. And when do we want to accept? If the reversal of the string is um, reaches the start state. So q0 becomes the new final state, and all the transitions are reversed. So transitions will look like this. Okay, so what we did is q0 becomes final state, and union of f is the new start state. And all the transitions are reversed. Okay, then you get an NFA for the reverse language. So is this fine with everyone? Yeah, if there are questions, let me know.
How can I prove the regular language are closed under reversal?
So you want to write this formally. Okay, so what do you mean by closure under reversal? So if I uh, yeah, if I give you an NFA for a language L, then you want to come up with an NFA for its reversal. So isn't that a proof itself?
Just you are saying, but I am thinking right now. So later I will confirm.
So how powerful this proof by construction mechanism is? Like in the theory of computation, most of the proofs are given in the form that since the construction is possible, like in this case also, since I can construct this, so therefore the regular language is closed under reversal. So how powerful this method is, moreover, how formal this method is to prove something.
Okay, so so one thing is that so proof by construction is one nice thing about it is that it is easy to verify. That I give you, for example, I give you a construction of NFA, and then you can always verify that it is correct. But not all proofs are constructive or are known to be constructive. For example, there are existential proofs, where if you want to say that some structure, if something about the graph is true, then some structure must exist. So one way to do that is to show that, always give you a constructive proof and show that such a structure exists, and you can verify that it actually exists. But such proofs are not known for many examples. there are some problems by Edish, the probabilistic method, where we don't know how to show existence of such objects. So what we do is we show that with non-zero probability, that um that object is guaranteed to exist. So we only argue in terms of probability. We don't know what the structure is and what it looks like and how to locate it. We only know the existence. And these problems are actually important in complexity, particularly because there are many problems where only existence is known. I think you've done this complexity course where we knew that existence of hard truth tables is known, but we don't know the explicit construction of it. So yeah so yeah I mean although constructive proofs are nice to have, in many cases we don't have them.
That's true, but like in this case, what's the guarantee that that this is not going to fail ever? Like if I follow this process, whatever I get will always result into the recognition of the reversal of the language.
Right. So for that, you need to write. So statements like these are not enough to convince anyone that this will always be um, accepting reversal. So for this, what we need is a formal proof of why this is correct. So yeah. So actually, you need to, yeah, just writing this is not enough. What we'll have to do is that we will have to show, the proof of this will be to show that L of is equal to yeah so I'll call this machine N, okay, and we'll have to show that this is exactly equal to there. So
Yes. And for this thing, do we need to go in both the directions, if and only if kind of situation?
yeah.
Yes. Yes. Right. Right. So I'll have to show that if I follow this process, then whatever string I get would definitely be the reverse of the language. Is something else. And it's one direction. The other direction would be what? That the forward direction would be that if the reverse of the string is given, then this machine is going to accept the reverse. The other direction would be that if I follow this mechanism, that whatever I accept indeed is the reverse of the string. Oh,
Ma'am, in this case, these both are the correct. All the string except by this NFA, and this NFA is formed for the string.
Sorry, can you repeat? I did not understand your question.
Ma'am, all the string in reverse except by this NFA.
Yes, that is what we want to show, that
Ma'am, these both are the correct in this case.
sorry.
Ma'am, B made a NFA for the what language? Particular NFA.
This is the NFA for the language.
Yes, ma'am.
Yeah.
And this language except by this NFA, then these both are the correct. And the reverse
Yeah.
was also correct.
Yeah, so what you will have to show is that every string that is accepted by this NFA is a reversal of some string in L, and
Yes.
yeah, for every string in L, the reversal of it will end up being accepted. That is what we mean by equality. It goes both ways.
Yes, ma'am.
Yeah.
Then it is also a proof, and why it is not proof?
Yeah, so what I'm saying is that this is the intuition why this should be correct, but a formal proof of this will have to mathematically prove that L of n is exactly those strings which are reversals of.
Ma'am, I don't understand why this is not proved. Oh.
Okay, so I mean this is just the intuition, but we will have to mathematically write every step of it. So for example, if I just write this, you are convinced that this is correct, but someone else may
Yes,
not be
ma'am.
convinced that this is correct. So in order for them to verify, we will have to write mathematically all the steps, and so that they can read and verify that this is exactly the automaton for reversals.
Yes, ma'am.
Okay, so yeah, can I move on to the next question, or are there any more questions? Okay, so let me do one thing. When I upload this PDF, I'll not upload it immediately. I'll write down a proof of this so that you can see, um, what these proofs would look like. Okay, yeah, it shouldn't be long enough. Yeah, I'll write this and upload it. Okay. Yeah. So here you are given an NFA, and yeah, we want to find out what is the complement of this, of the language accepted by this NFA.
Ma'am, D option.
Okay, so let's wait for others. Yeah, if you have answers, either unmute and let me know, or you can use the chat box. Yeah, any other answers other than D?
A star.
Okay. Mm, okay. So yeah, let's find out. So let's just find out what is the language of this NFA. Then we will. It's easy to complement it. So what is the language of this NFA? I'll call this NFA N. Okay. So A is accepted. So A is in the language. What about AA? A is accepted because I'll take on A, I'll go from A to B, then we'll make epsilon move to C, another epsilon uh, move to A. So we are at A. Now I can read another A and go to B and accept. So AA is also in the A square is also in the language. Similarly, any number of A's here, A to the K, we can do the same process K times. So all of this is in the language L of n. Okay, and what about epsilon? Is epsilon in L of n? Well, there is no epsilon move from the start state A to final state B, so epsilon is not in the language. So yeah, so complement of okay, yeah. So is everyone does everyone agree, or are there any questions?
Yes, this seems right. And since this is NFA, so we cannot directly apply that we make the non-final is to final and final into non-final. That is not to work here because this is
Yes.
NFA.
Yes. Yeah, so in this example itself, if we make A and C final but not B as final, then
No, that won't work because then in that case the epsilon will become the part of it.
correct. Yeah. Okay, good. Are there any other questions?
Ma'am, if the single element epsilon in the set,
Yeah, so when we say sigma star, okay, we are only talking about uh, all the elements over A. Epsilon is not in the alphabet. Does that make sense?
ma'am, language except by A is also epsilon is also in this that language.
Yeah, so that's what I'm saying, that I'm only talking about strings over A.
Yes, ma'am.
Okay, so that's why we generally don't write epsilon as a part of sigma. Even in the definition of NFA, we wrote sigma union epsilon.
Yes, ma'am.
Okay, yeah, good. So, okay, let me just, okay. Okay, so we are given this NFA and we want to convert it into a DFA. So the standard method that we know is subset construction. So what I'll do is we will write all the subsets of 1, 2, 3. So we have yeah, so there are 8 states, and what we'll do is yeah,
Ma'am, phi 1, 2, 1, 3 state are in NFA. Four
sorry.
state. Phi state 1, state 2, and state 1, 3. DFA.
Oh, you are saying that these are the final states.
No, ma'am. DFA में in DFA state are phi, state 1, state 2, and state 1, 3. Four state in DFA.
Yeah, we are not asking for the minimum DFA. We will just follow the construction that we know, right? The subset construction method, where we write all the sets, all the subsets, and then
Yes,
we will
ma'am.
see the minimum one.
Uh,
Yes.
no, but even in the subset construction method, we won't be considering all the states. We will start from the initial state and we will only consider those states which are the reachable ones.
Oh, okay. So, okay. There are several methods. Yeah, there are several methods for the subset construction. The one that I am talking about is, yeah, is that you blindly make all the subsets and then add transitions and remove the ones that are redundant. Yeah. Whereas, yeah, if we do what you are saying, then you'll not create those states in the first place. Yeah.
So can we use the second one? Say only let us consider only those states which are the reachable ones.
Hmm. Yeah. Sure. So you're
So in that
saying,
case, yeah. So we will start from the initial state one, say.
hmm.
But in this case, since there is an epsilon move from 1 to 3, so in fact the initial state will
Okay. So
become
let me just remove all of this. Hmm. Yeah, so we'll do an epsilon closure of 1.
yes. So then the 1 comma 3 becomes the initial state.
Correct.
Can you draw, not, I mean, instead of this, can you draw the table? That would be easy to, I mean, right,
Mm,
transition table, and then we start from the 1 comma 3 as initial state. That would be
so
easy.
what do you want on the left hand side?
So 1 comma 3 state, and the transitions we would be making for the A and then B. These are the two options
Okay.
here. So after getting, say, A on the state 1, so we will be considering 1 and 3 because, yeah, because there is an epsilon move from 1 to 3. Okay.
Yeah.
And then after getting 1 on A,
Hmm.
so what should I write? So after getting 1 on A, what is the epsilon closure of 1? So epsilon closure of 1 is 1 and 3.
Hmm.
So if that is the case, so then I can move from after getting A on 1,
Hmm.
I'm moving nowhere. But then after getting A over 3, I'm moving to 1.
Hmm.
So, and then I need to take the epsilon closure again. So in fact, I would be applying the epsilon closure two times here
Hmm.
to find the transition for 1 comma 3.
Hmm.
I hope this is right. So for 1 comma 3, I will compute what? So therefore, after getting 1, I shall make the move to the state 1 comma 3 only.
Okay. So I'll just repeat whatever you said. Okay. So we are at state 1, 1 comma 3, and we'll take an epsilon closure of this, which means on reading epsilon, where do we go? So from 1 we can go to 3. From 3 there is no transition, so we are in this state. Now we will make a transition on A. So 1 on A there is no transition defined, but from 3 we can go to A, so we can go to 1. So this is where we are, and again we'll take an epsilon closure of this, so that gives us again 1 comma 3. So by the way, there are two methods, at least two methods of doing this. One is that you make the transition first and then take an epsilon closure. The other method that you have probably seen in class is that you take an epsilon closure first, then you make the transition, and then finally take an epsilon closure. So that leaves us with 1 comma 3. Okay. um yeah, can someone, yeah, tell what should be the entry in this?
2.
2. Okay, so from 1 on B we go to 2. From 3 on B there is no transition, and if we take an epsilon closure we are at the same. Sure. So now you're
Next
saying,
stage is 2.
hmm, correct. So
Yes, ma'am. 2 1 A 2
yeah.
and 3. 2 and 3.
Hmm. 2 and 3, because 2 on A there's a transition to 2, and 2 on A there's a transition to 3. If you take epsilon closure also, you will end up in the same states.
2 1 B 1 3.
2 1 B 1 3. Yeah, correct. So we should add 1 3, sorry, 2 3. Okay,
2 3 1 A 1 2.
2 3 on A, go to 1 2, correct.
2 3 1 both 3.
Now we have one more state 3 and 1 2 also.
Ma'am, can we write 3 at 1 3? 3 S.
Can you write 3 as 1 3? No, I think as subsets these are different.
Okay, ma'am.
What's the question?
So it's asking
मैम
whether
2 3 1 B 3 की जगह 1 3 लिख सकते हैं.
What did he ask?
so I think he is asking whether we can write
2 3 1 B.
okay, I think then I didn't understand. What I thought earlier was that he's asking that 3, whether 3 can be written uh, as its superset 2 3 or 1 3.
No, that cannot be written.
Yeah.
Now the next reachable state is 3, and then we should consider the transition from the state 3 only. So after getting A over 3, the transitions are made for the state 1 only. And then 1 comma 3 will become, I think.
Yeah.
And similarly for B, it is nowhere. So it is 5.
Sorry,
No,
yeah.
5. And now, which is the next reachable
No,
state?
sorry. From 3 you take an epsilon closure. Okay, you will still not go to, correct, okay.
Yes. So it is 5. And then is there any new state here?
No, but yeah, but we have to
Write it for,
finish for 1 2.
1 comma 2 is remaining. So for 1 comma 2, the closure of this one is 1 comma 3. And so then 1 comma 3 will definitely come. And yeah, 1
Now
comma
if
3
it,
will definitely
sorry.
come. And 2 after getting A is what? So it is 1 2 1 2 3? Not sure. We need to
Okay, so
check.
from 1 there's no transition. From 2 you go to 2 comma 3. From 3 there's a transition to 1. Yeah. And if you, even if you take epsilon closure, you will get 1 2 3. So we have 1 2 3. Yeah.
And for B, it is after 1 comma 3, it is 2 only. I can reuse the values from the previous rows. So in that way, it is 2. And what else? What else is remaining? It's not visible actually. So from, yeah, I mean, yes, it's visible now. And can you go slightly down in the slide so that I can see the last row? For which state are we considering transition this time? So we are
Oh yeah, we are
considering
looking at 1 2 on B.
1 2 only. Oh, I see.
Yeah, but epsilon closure of 1 2 is 1 2 3. So from 1 to 3 we are going to B.
Oh, so I need to look for additionally. So for 1 2, I'm making 1 3, I'm making transition to 2. And then for 2, after getting a B, I'm making transition to 3. So therefore, it will be 2 comma 3, I guess.
Yeah, and if we take an epsilon closure, we are still at 2 comma 3.
Yes.
So this is 2 comma 3, but now we have a new state
1 2 3.
1 2 3.
So for A, it would be 1 2 3.
Yeah. What is the epsilon closure?
epsilon closure of 1 is 1 comma 2 is 1 2 3, and apart from this 1 comma 2 I have additional 3 here, and the epsilon closure of 3 is 3 only. So therefore 1 2 3 epsilon closure is 1 2 3.
Now
Therefore,
on A, yeah.
yes, so for 1 2 3 I can reuse this 1 comma 3, the very first row, wherein I am moving 1 comma 3. Additional, say for the value 2, I can refer the second row.
Yeah.
Collectively, this will give 1 2 3.
Hmm.
And similarly for B, from the first row I will get 2, and then from the second I will get 3. So 1 2 3. Yep.
Correct. And even if we take epsilon closure, we'll be at 1 2 3. So we have 1 2 3 and 1 2 3. Yeah.
And now, so this is the DFA is ready. And now, if at the most, if you want, you can write 5 and then 5 all last row, all 5 values, if at all, if it is required. Otherwise, this is the DFA now. So how many states are there in the DFA? 1 2 3, starting from the first state. 3 and 3 6. 1 2 3
Yeah,
and 3
you are
6.
right. So for phi also we need to make
Yes.
transitions. Yes. So for the empty set, uh, yeah,
So 5 5, nothing else,
nothing.
nothing
Yeah,
else. Yes. So there are, in total, there are how many states? If we count the number of the states, you have 3 and 3 6 plus 1 7. So
7
one
states.
state is not reachable here. Out of 8 possibilities, one is not reachable. Yes.
yes. So out of these, I'll only
Moreover, the final state is remaining. Which
yes.
state will be?
So which states are final? Mm,
So
all
since one is final here, yeah,
one and yeah. So 1 3 is final. 1 2 is final.
that's and 1 2 3 is
1 2
final.
3 is
So while determining this final state, now I need not to look into the epsilon closure of one, because this mechanism is designed in such a way so that wherever we find one, one will always be accompanied by its epsilon closure
final.
step. Right, right,
Yeah.
yes.
Yeah, and the start state is 1 comma 3. So this is the start state, and the blue ones are the final states. So 1 3, 1 2, 1 2 3. These are the final states. Okay, so okay, are there any questions about this?
Ma'am, I don't understand when B check state 2 3 to B. Uh, it can be 3 or 1 3 both.
This one, this
Yes,
entry,
ma'am.
uh,
Yes, ma'am.
2 3 on B. Okay, so let's calculate this again. So epsilon closure of 2 3 is 2 3 itself. From 2 3 on B, from 2 on B we can go to 3. Yeah, so from 3 there is no transition on B,
Yes, ma'am.
right? So this is all that we get, right? So from 2 on B we get to 3, but from 3 there
Yes,
is
ma'am.
no transition on B.
Yes, ma'am. It is another next state 3. Then we constructor DFA.
I couldn't hear you, sorry.
It is state 3 is a new state when we construct the DFA.
uh, this
Yes, ma'am.
Yeah, so then 3 is the new state and we expand the table. Yeah,
Yes, ma'am. ठीक.
yeah, good. Okay. um Yeah, I think I had one more question, but in the discussions earlier, we already answered this. That for a DFA, if you switch the final and non-final states, then you have a DFA for the complement language, but the same is not true for NFAs. I think even in this example, if we switch the final non-final state, we um, will not have an NFA for complement language. So yeah, I think that is all I had for today. Are there any questions about anything that we covered so far?
Can you explain or elucidate the theoretically how to convert the NFA to DFA?
Uh, as in, you mean the general method, or what do you mean by theoretically?
Ma'am,
Just how to formula how I will got obtain the 1 3 from transition input A for a transition 1 3, how will this getting from?
Yeah, sure. So the general method um, is that the start state is going to be, let's say S is the, let's say, yeah, let's say S is the start state of your given NFA. Q sigma union, what is it? Yeah, F and S. This is the NFA you started with. The new start state will be epsilon closure of S. Then the final states are going to be all the states in the, let's say N2 is the new NFA that we obtain. Final states are going to be all those state Q such that there exists some final state in the previous automaton, and P is contained in the tuple Q. Because these are actually subsets, right? So these are subsets of Q.
This N2 is DFA, or this
N2 is
N2.
NF, is DFA, correct? Yeah,
Yes, yes. So, I mean, this is new NFA is written
yeah,
here.
yeah, sorry.
Yeah.
Okay. And what are the transitions delta? So transitions are that from a state Q, you first do an epsilon closure of Q. Sorry, I should write comma A. Then you take a transition of those states. So this is slight abuse of notation, because here EQ could be a set. There could be multiple elements there. When we write this, what I mean is for each of them you take transition. Is that okay, or should I write it better? So
Nick, I'll explain more and then I'll be better understand.
yeah, sure.
So,
Okay, so
but somewhere a union symbol should also occur here.
yeah, here, I mean, this is a shortcut thing that I did, but yeah, let me write it uh, completely. So okay, so first you take an epsilon closure of Q, then uh,
then I take its delta. Then I take delta of epsilon closure of Q comma A.
Yeah, but
And
these could be multiple states.
right,
So
right,
you
right,
want for all of them. So okay,
right. So
let's
delta
write it step
closure.
by step. So
Yeah,
first find out the epsilon closure of Q. Second step would be for all P in E of Q, find out delta of P on A. Okay, and take a union of all this.
right, right.
Okay,
Yes.
and third step would be to find the epsilon closure of uh, for all P prime in, or let's say P itself, for all P in union of delta. Maybe I'll just call this new set as, let me call this new state as new set as S. So for all this for all the elements in this set S, what we'll do is we will take an epsilon closure of P and take a union of all that, and this is the final output of. So let me just explain once. So we want to find out transition of Q on A. So what we do is first take an epsilon closure of Q. So these could be multiple elements. For each of those elements, we will find out the transition of that state on A and take a union. So store all of them into the set S. And for each set P prime in the set S, we will take an epsilon closure and merge them together, take a union, and that is our final delta of Q of A. So that is what we did here. First we took a epsilon closure, then we made the transition, both of them took a union of that, then we took an epsilon closure, and that's our final answer. So is this better?
Yes, thank you, ma'am.
Ma'am, I
Yes.
want to ask if we have two DFA, we can connect the DFA in parallel to we find a union. If we connect one after other, we find concatenation. I mean, how we find the intersection of these two language?
Yeah, so for NFAs you can directly add epsilon transitions, and at least union was clear, intersection we need to see again. I need to see.
Ma'am,
But
I ask for
DFAs,
intersection.
but for DFAs, right?
Yes, ma'am.
Yeah, so for DFAs, the product construction is what we generally do. So if you have two DFAs, then yeah, so for DFAs, let's say you have M1 and you have M2, and we want to find a DFA M such that L of M is equal to L of M1 intersection L of M2.
Yes, ma'am.
Right. So one standard method of doing that is what is called product construction. So let me write this formally. So what we do is M1 is Q1, you have delta, sorry, you have sigma, you have delta 1 F1, and let's say Q1. M2 is Q2 sigma delta 2 F2 and Q2. Note that the alphabet here must be the same, otherwise the question
Yes,
is not
ma'am.
well
Yes,
defined.
ma'am.
Yeah. So the product construction for intersection of these languages is that you form a new set of states, which is basically a tuple. It contains two elements. One element is from Q1, the other element is from Q2. So how many states will be here? this will be size of
Q1
q1
into
times size of q2
yeah.
many states. Okay, and alpha bit remains the same. We need to define what is delta. Okay, and what are the final states?
Ma'am, both state final
Yeah,
Q1 Q2.
so yeah, so it is the, yeah, let us define it now. Yeah, the start state is definitely going to be the start of both of them, which is q1.
Ma'am, simultaneously both मतलब both be final.
Yeah, I'm coming to that. Yeah, so the final state should be the set of all p comma q, where p is in the final state of the first DFA and q is in the final state of the second DFA.
Ma'am, it is or.
Yeah, for intersection this is and, um, because you want both of them to hold, both the conditions to hold.
Okay, ma'am.
Okay, so this is for intersection, but if this is for union, then can someone define what should be f?
Or P
Or,
is the element
exactly.
of
So
it.
here we have and, here we have or q in f2. And one thing that remains to be done is to define this delta. So delta of pq is delta 1, sorry, let me write it again. So delta of pq on a symbol A is delta 1 of p on A and delta 2 of q on A. So basically what we are doing is we are simulating both the machines. P is the state of the first DFA. On first DFA, if you are at state P and you see an A, then where do you reach? Similarly, if you are at state Q in the second DFA and you read an A, then where do you reach? This is uh, governed by delta 1 and delta 2 respectively. So this gives you the first element of Q1 and this gives you the element of Q2. Is
So
this okay?
is this a sufficient proof to show the closeness of the regular languages under intersection? Say for example,
Yeah, so this is not proof, this is just the construction. But to prove this, to prove this, we
wouldn't
will,
wouldn't be the proof by the construction kind of the thing? And since the very construction of this machine is possible, and there is only one way to show the or to prove the regularness of a language, that if the construction of f is possible.
right.
And
So yeah, so construction is there, but what we will need to argue, like we said earlier, is that the language accepted by this new machine, this new DFA M, is exactly same as L of M1 intersection L of M2. So it's just that we need to mathematically arrive at this statement that this is exactly what we are accepting.
yes, right. Yes, but since synergistically we are executing both the machines, I
True.
don't know whether both the machines are being executed parallelly, or I mean, in what order are they being executed? But then the situation is like this, that both the machines are getting executed somehow. Parallelly, probably, I don't know.
Yeah. So at one step itself, we are. Um, so each state remembers more information now. We are simultaneously making both the moves, sort of, at the cost
Yes,
of memory. We have increased the number of states.
Yes, because now every state has got something from the first machine and something from the second machine. Yeah.
Yeah.
Yes, yes, right, right. Yeah, true.
Are there any other questions about anything?
Ma'am, I want to know what are the initial steps if we have two uh, DFA and how we construct a DFA of intersection array.
What are the steps
Yes,
to
ma'am.
construct the intersection of DFA?
Yes, ma'am.
Uh, yeah. So yeah. So first step would be, maybe is it better if we take a small example, or what do you prefer? Okay. So okay, let me just take a one very small example. Maybe um, so this is a DFA which accepts even number of zeros. This is M1, and let's say this is M2 which accepts mm, sorry, odd number of ones. Okay, so now we want to construct
No, no, no. This is accepting even number of the ones.
right, sorry, this is odd.
So, but then you can design M2 like say accepting that the so like M1 is accepting wherein the number of zeros is divisible by 2, and then we can take M2 wherein the number of ones is divisible by 3. That would be a triangle kind of the structure, nothing more than that.
Yeah, we can.
And then we can design a new machine which accepts all the strings wherein the number of zeros is divisible by 2 and the number of ones is divisible by 3.
Sure. Okay, so let's call this mm, 1
Two
2.
more two more self loops are remaining with the zeros.
Okay,
Yes,
so
yes.
this
No.
is A B C. So what are the states? Step 1 would be that you make all the states. Okay, so the states are mm, yeah, 1 comma A, let me write it, 1 comma B, 2 comma A, 3 comma A, 3 comma, sorry, this should be ABC, right?
No, no, no. There
Sorry,
would be
what am I
six.
doing? Sorry.
There would be six states only, and better you name these states as P and Q. So then it would be easy. Say PA, PB, PC, and then QA, QB, QC. There would be six instead of writing one and two here, because one and two the state names are also one and two. So instead of writing the state names as one and two in the first machine, uh, you can write the name of the states as P and Q. So that would be easy to identify. P and Q, yeah.
Okay.
And now the states would be PA, PB, and then PC, and QA, QB, and QC. There would be six states
QA,
possible.
QB, Q. Sorry,
PA,
let
PB,
me
right?
just write.
It's okay. It's okay. PA, PB, PC, then QA, QB, QC, right?
Yeah, and the start state will be the start of both of them. So P and A. So P comma is our start state. And what are the transitions? So P on 0 goes to Q, and so will be somewhere among these three. And A on 0 stays at A, so we will be at Q comma A on 1. Similarly, from, sorry, this is not okay. And let's do P comma B. So P on 1 stays at, sorry, we are doing 0, right?
0, yes.
Yeah.
And instead of considering PB, we should start with QA only, because only the reachable states are going to be considered. Because
Mm,
this is not necessary, like say here we
so
have six
these,
states. Uh, so quite possible that if we take the Cartesian product of Q1 and Q2, then all the states may not be reachable.
yeah,
Any states
that
will
is,
become redundant.
yeah,
So, I mean, while considering the further transitions, like in this case,
yeah,
we may
sure, sure,
consider
yeah,
reachables only.
yeah. So from, okay, let's complete the transition of PA on 1. So P on 1 stays at 1 and A on 1 goes to B. So we should be at PB. Then let's do a transition on QA on 0. So QA goes to P, Q on A goes to P, sorry, Q on 0 goes to P, and A on 0 stays at A. So we have a transition like this. And so can someone finish this QA on 1?
So QA on 1 would be, so the design would be very, very symmetric. So what you can do is, uh, say after getting Q on 1, is A on Q, after getting 1 on A to B, so QB.
Yeah.
So after getting 1, say QB, and 0 has been defined. So now from PB, after getting a 0 to QB, and yeah, like this, and after getting a 1 here, that's right.
Yeah,
After getting
that
1
should
on
be,
PV, yeah, like this, and from on QB, like this, there would be a subtle, yeah, from QC, yes, after getting 1, and then, yeah, right.
yeah.
And PQ becomes a final state.
Hmm. PQ becomes the final state. No, Q and A becomes the final state.
So,
Sorry.
will become the, like in this case, so P should become the final state in the first machine to recognize all the strings in which we have even number of the zeros,
Yeah,
number of
so here you have, sorry, we changed the example. So we made this odd number of zeros and even number of ones.
no, the problem
Sorry, this is
was
not even. This is
uh,
uh,
number of
multiple
A's
of
is
3.
divided by 3, and in the first machine the number odd number of the zeros. Okay, so in that case the QA will become the final state, right?
Yeah. Yeah, sure. So, are there any questions?
No, ma'am. I understand.
Ma'am, I have a one question. So
Yeah, go ahead.
construct a non-deterministic finite automaton accepting a b, comma ba, and use it to find a deterministic automaton accepting the same set.
You have an NFA for AB, BA. Okay, and you want to make a DFA out of it.
Find a, yeah.
Okay, so, okay. But what is your NFA? Because
Ma'am, I think AB star BA star is this.
this is what you want.
No, ma'am, I don't. This is another one who want to.
So, so what is the NFA that you have in mind to start with? Okay, I guess I think you have epsilon move on.
Yes.
Okay, but okay, sure. So let me call this 1, 2, 3, 4, 5, 6, 7. Okay, and now you want to use the subset construction method to find a DFA out of this. So let me just okay. So what is the table? You start with you start with
1 to 5.
2
This is
5.
going to be very, very lengthy because there are 7 states here. 2 raised to the power 7. Even though, the table would be lengthy here. Anyways, but we can start with 1, 2, and 5. Let us see.
Yeah, although the DFA here is, I mean, very obvious to construct directly without doing the table, but yeah, sure, let's do this. So yeah, maybe it would be easier to consider just AB, but okay, fine. So epsilon closure of 1 to 5 is 1 to 5, and then we make a transition on A, so that would take us to 3, that's all, and epsilon closure of 3 is just 3. Then the transition on B would be from, yeah, there's only one transition, so you go to 5. Then the new states that you have is 3 and 5. So from 3, the epsilon closure is just 3. And from 3 on A, there is no transition. So we go to phi. From on B, we go to 4. Sorry, did I write? Yeah.
But for 1 to 5, after getting B, so after getting B, say even from the state 5, we are moving to 6, isn't it? And then so it should be instead of 5, this should have been 6, I guess. 6 in the first
Oh,
row.
okay, sure. So from 1 to 5 on B, we go to 6. Yeah, thank you. So this should be 6. So this is 6. Yeah. So from 6 on A, we go to 7. From 6 on B, there is no transition. From 7 on AB,
5.
there is no transition.
And
So
one more
that's
for
all. Yeah.
one
4,
more for
4.
5.
Yes.
5. And this is a very good example seems wherein we have lesser number of the states in the DFA.
Yeah.
Yes, yes, right.
Yeah. So on 4 also, there are no transitions further. So let's draw this DFA, or yeah, okay, let's do it. So 1 to 5, this is our start state. On A, we go to 3. On B, we go to 6. From 3, there is a transition to phi. On B, we go to 4. From 6, we go to 7. On B, we go here, and then you have AB. And what are the final states? Final states are 4 and 7.
So if we do not show these transitions towards the 5 state, towards the 6 state, then this is a clear DFA. I mean AB and then B is stuff.
But if we don't have these, then we are violating the definition of DFA.
But then in the construction of the DFA, this sync state need not to be explicitly mentioned. Even if it is not mentioned, by
Yeah,
default, it is implicit that we are moving to the
yeah,
making move.
that is sort of for the sake of brevity, because otherwise the diagram becomes clumsy. But if you just look at the 5 tuple definition, then you are, because delta is a function from q cross sigma to q, so for every q, there must be a transition to some q by the definition of function. But yeah, I mean, for the sake of drawing, we need not draw.
Yes, yes, right.
Yeah. Okay. Um, so it's 8:50, right? Maybe we'll wrap up for today. Next we will meet on Monday 7 to 9 p.m. same time.
So would you be covering Myhill-Nerod in the next session? If you can give slightly more, few more questions on the Myhill-Nerod.
So this is not in the lectures, is it?
It is
Oh,
there
it
in
is
the
in the
week.
lectures. Okay, sure. Then yeah, we will have some examples. Yeah.
Yes, right. Yeah. All right. And especially the difference in between the Myhill-Nerod and the pumping lemma. And so
Okay, both are two different methods to prove that a language is not regular. So, what do you mean by difference?
so difference in the sense that I mean, what's the actual use of Myhill-Nerod? Minimizing DFA and or proving non-regularity in that sense. And moreover, what is the relation between these two things?
Okay, sure.
All right. Yeah. Thanks.
Okay, thank you all.
Thank you, sir.
Thank you, ma'am.
Yeah. Bye.
Bye.
Thank you, ma'am.